Okay, but what about the symmetry one, right? That's probably, I mean, that's a little bit tougher. So here's the symmetry question. All right, there's our function. Let's make that a little bigger. Okay, there's our function. And we're supposed to determine what the symmetry is. Okay, first of all, what are our tests for symmetry? What's the even test for symmetry? F of negative x equals f of x. Okay, good. Oops, what happened there? Don't know. So f of negative x equals f of x. Okay. What's the test for odd symmetry? F of negative x equals negative f of x equals the opposite of f of x. Okay. Oh. Okay. Okay. So what are our options then? If we wanted to figure out what the symmetry of this thing is, one option would be multiply out the whole thing and apply the test for symmetry, right? And all we'd have to do, if we multiplied out the whole thing, we wouldn't even have to apply the test for symmetry because we know, how would I know if a polynomial has even symmetry without even applying those tests? What would be true of the polynomial, of the powers of x? They would be what? The exponents would be, if it has even symmetry, they'd be even, right? All of the exponents would be even. So the exponents would be, 0, 2, 4, 6, etc. But none of the x's would be to an odd power. Obviously, if looking at the polynomial, if all of the terms only included odd powers of x, then we know it's an odd polynomial, right? It's got odd symmetry. So for polynomials, these tests are really simple, right? But the first one, expanding out that polynomial, we're going to bail on that. That's too time consuming to multiply out the whole polynomial, right? There might be a better way. Okay, could we apply the symmetry test without expanding? I mean, we could, right? So what would, but it's kind of tough. F of negative x is going to look like negative 2 times negative x quantity cubed times negative x minus 3 quantity squared times negative x plus 5, right? Okay, so that's kind of tough to do because we could realize that that's going to be like negative x quantity cubed becomes a negative x cubed, which is going to turn that into a positive 2 x cubed. Negative x minus 3 quantity squared is the same as negative 1 squared times x plus 3 squared, right? Negative 1 squared. So I could write that as just that. And then this guy here, if I factored out a negative, make that negative, and that becomes x minus 5. I mean, we could potentially do something like that and then apply that, but that's pretty hard stuff, right? I mean, there's a lot going on there. We're not going to mess with that. Are there easier ways? Yeah, there are. There's two much easier ways that we could use without having to do all that math. Okay, what's the way that we kind of agreed on Thursday? Remember? For these symmetry tests, what's that mean? It means that if I plugged in f of x, if I plug in some positive value of x, just pick one, and then I plug in its opposite, its negative opposite, one of these two things would have to be true of the numbers I get. Either when I plug in the negative number, I'm going to get the same as the positive number, or I'm going to get the opposite of the positive number, right? So why couldn't we just pick a random number, plug it in, and see what happens, right? And just see if it is going to honor one of those tests. Okay, and maybe right away we'll get an answer that's obvious. Okay, so we could try a convenient opposites like positive 2 and negative 2 or positive 3 and negative 3, but we want to pick ones other than zeros. So we'd want to avoid x equals, man, what's this thing doing? We'd want, There we go. We'd want to avoid 3 or 3 and negative 3, 5 and negative 5, and 0, right? We'd want to pick something like 1 and negative 1. Plug those in and see what happens, right? So if we apply that test, we could do what's f of 1. I can plug f of 1 in, and we're going to get negative 2 times 1 cubed. So I get negative 2 times 1 minus 3 is negative 2 squared is 4 times 1 plus 5 is 6. So that's giving me negative 48. Now let's try f of negative 1. If it's even symmetry, what would we expect for an answer? If it's even symmetry. Same, right? We'd expect f of negative x to be the same as f of x, so we'd expect 48. If it's odd symmetry, we'd expect negative 48. Let's see if either of those happen. So f of negative 1. Well, negative 1 cubed is negative 1 times negative 2 is positive 2. Okay. Negative 1 minus 3 is negative 4 squared is 16. And let's see, negative 1 plus 5 is 4. So I'm getting 32 times 4. Well, that's not either one of those, is it? 32 times 4 is 128. So we can see that it's got to be neither. Agreed? Okay, isn't that quicker? Right? Okay, the other viable option I would say would be use the graph. What does even symmetry look like on a graph? What's even symmetry? Think about the easiest even function, x squared. What kind of symmetry does it have? Yeah, going to be that line symmetry or folding symmetry about the y-axis. What does odd symmetry look like? Rotational symmetry about the origin, right? Yeah, so that'd be an example, that'd be like x cubed, right? We have to rotate it 180 degrees to make it line up with itself, okay? So we could graph it and see what happens. Now, that would only make sense if you were graphing it for some other reason, because that's probably a lot of work to graph it. But in this problem, what do you know? They're asking us, if we look down to the next part, they want to know what the graph of the function looks like. So we could just use the graph to determine the symmetry also, right? Okay, so let's do the last part then. Let's do the graph. You guys already told me the x-intercepts. Okay, you told me the x-intercepts were 0, 3, and negative 5. Okay, so what were my colors there? 0, green, blue, orange. So 0. What was the next? God, I forgot already. What is it? 3 and negative 5. 3 and negative 5. So those are our x-intercepts. You told me what they do, right? You told me the behavior. So we said that we are going to cut like a line at 5. We're going to bounce at 2 and cut like a cubic at 0. I mean, bounce at 3. I think I said 2. Okay, but we need end behavior. Well, we already got end behavior. We calculated that. It goes down, right? So if we combine all that stuff, we should be fine. We know the end behavior is doing this. At 5, we are bouncing. So that means when we shift to blue, it's got to do that, right? At green, it's cutting like a cubic, right? So at 0, it cuts like a cubic. So what's it going to do here? When I switch green, what's the graph going to do? Okay, good. It's going to have to flip over to go through x there, but it's got to go through x like a cubic. So it's doing that, right? Give me 1 to 5 so far. How are we doing? Okay, and then the last one at negative 5, it's cutting like a line, right? So then what's it going to do when it flips orange here? Kylie, what's the behavior going to be once if I flip into orange mode at that point. What do I got to do? Who can help me out? Ashton? It's got to go down to cut the x-axis, and it's going to cut like a line. And there we go, right? That's pretty ugly, but you get the idea? Okay, give me 1 to 5. How are we feeling on this? Okay, all right. Okay. And let's see. Last one. Okay, one like this. So this time they're giving us a polynomial, but it's not in factored form. Okay. So we're going to have to factor this thing. Now we haven't really practiced. That's what the next part of our unit revolves mostly around factoring polynomials. And we'll get some practice. There's some different techniques depending on what they look like. But this is one we can do. This is one we can do from stuff we already know about factoring. So how would we factor this? What do we always try to do first when we factor? What do we always try to do first when factoring? Yeah, GCF, right? We always want to factor out the biggest GCF. So what is our biggest GCF? X squared. Okay, so we could factor out an x squared, leaving us with what trinomial if I undistribute an x squared? What are we going to get? Ella, what are we left with if I factor out an x squared? Plus, 49. You're already thinking ahead. Yeah, there you go. Plus 49. Okay. And so now there's our GCF. We've got a trinomial, a quadratic trinomial. So what are we going to look for now? Magic numbers, right? We're going to see if we can factor that trinomial. Are there magic numbers that multiply? Are there magic numbers that multiply to 49 and add to negative 14? Yeah. What are negative 7 and negative 7. Okay, good. So then we end up with f of x equals x squared times, my magic numbers are x minus 7 and x minus 7. So how would I write that factor then? Squared. Good. X minus 7 squared. And if we set this equal to 0 to find the x-intercept, what are our zeros then? 0 and 7. Good. Okay, so we get x equals 0 or x equals 7. Okay? Okay. What's the multiplicity of the leftmost 0? So if I were to graph this thing, which of these, 0 or 7, which is leftmost? 0. Yeah, that's further to the left on the x-axis. So what's the multiplicity of the leftmost 0? 2. How about the rightmost 0? 2. Okay, so what does it do at the leftmost 0? Is it going to touch the x-axis and turn around, or cross the x-axis? Touch and turn around, which is the same thing as what? Touching and turning around, how do we say that? Bouncing. Yeah, they're going to bounce because the multiplicity is 2. So we get it's going to bounce at the leftmost 0. How about the rightmost 0? Bounce, yeah. Same thing, right? Because it's also got an even multiplicity. Okay, give me 1 to 5. Okay, that's it. That's it. Anybody want to test today, or would you prefer to start tomorrow? But I'll let you do it today if you want to get started on it. Okay? All right, I'll give you the rest of the period then to work, ask questions, and we'll go tomorrow.